In this module, we will talk about molecular orbital theory, which is another way of looking at bonding in molecules. It's a different treatment, so you'll find that we do things differently than we did in previous models, such as valence bond theory. And as we get into this intro, I will talk a little bit about why we do molecular orbital theory, so that it hopefully doesn't seem just like one more thing we're asking you to learn for kind of no reason. And I don't know if it will come across as much in a video lecture as it does in person, but I kind of love molecular orbital theory, so apologies in advance if I get super excited about this stuff in this video. I think molecular orbital theory is super cool. Okay, so let's talk about what's going on in MO theory. So you'll see us abbreviate this a lot just to make things a little bit easier. So what we do is we mix together atomic orbitals, and we're going to keep the abbreviations coming here. So atomic orbitals, or AOs, on adjacent atoms, and I'm going to underline adjacent here. It's going to be one of the key differences between MO theory and what we did in valence bond theory. Because remember, valence bond, those orbitals we mixed together were on the same atom. Now we're doing it on adjacent atoms to create molecular orbitals which we abbreviate MOs. What we're doing is officially called LCAO, which is linear combination of atomic orbitals and like it sounds, these molecular orbitals cover and can cover the entire molecule. So this lets us set up some pictures showing how bonding electrons can be delocalized over an entire molecule. Now, before you get too worried, we're only going to do diatomics with molecular orbital theory. Going beyond a diatomic requires computing power, so we need computer programs to do some of these calculations for us, or we need there to be some type of symmetry, and then we have to do a whole bunch of matrix algebra, which again, one of my absolute favorite things in the entire world, but I'm not going to subject you to it here. Okay, so the big question, why are we even doing this? And the reason that we're doing this is because valence bond theory can't answer everything. So first of all, it fails to predict certain properties. So one of these cases is O2 is something called paramagnetic. And paramagnetic means it has unpaired electrons. But nothing that we have done with O2 up until this point could possibly show us unpaired electrons in this structure, right? If I draw a Lewis structure for O2, this is what it looks like. Everything is paired up. I've got bonding pairs and lone pairs, and I don't have a way to properly show where the unpaired electrons are in this type of structure, but in MO theory, I will be able to. Okay. the other thing where valence bond theory fails, so experimentally, the CH bonds in CH4 are not identical. So if you remember, one of the arguments to get us into valence bond theory was that the BEH bonds in BEH2 were identical. So they had to be made with the same types of orbitals because the experiment was telling us that they had the same energy. Well, now the experiment is telling us it doesn't match for CH4 the type of picture that we drew in valence bond theory. Right? In valence bond theory, we had the same type of orbital on carbon overlapping with hydrogen's 1s, but the experiment says it's not so. So it's not identical, but valence bond theory doesn't have the ability to show this. Now, CH4, you can see, is not diatomic. So this is a molecule that is too big for us to deal with at this point. So we won't be able, with MO theory, to prove the CH4 piece wrong, but we will be able to work with O2 and give you a little bit of a taste of this. All right, so this is the what it is and the why we do it. So the question is, how do we do it? So first of all, look at adjacent atoms. And again, I'm going to remind you, this is for diatomics only. Then you mix or add together. We're going to do this pictorially. Orbitals of the same type from each. And the reason we do this is because of energy. So things have to be about or close enough to the same energy in order to add together. And then there's this other component of symmetry, which you probably have some understanding of. We mean it in a really specific way when it comes to MO theory, but essentially, as long as you're always mixing the same type of orbital with the same type of orbital, you'll be good. So that means we're going to use the S on element or atom 1 and add it to the S on atom 2. The PX on atom 1 will add with the PX on atom 2. PY on atom 1 plus PY on atom 2, and I'm going to say etc., but the only thing left is PZ on atom 1 plus PZ on atom 2. Okay, so then next, when two atomic orbitals mix and form two molecular orbitals, one is lower in energy, and we call this the bonding combination or the bonding molecular orbital, and one is higher in energy. So overall, they're going to balance out. We'll have conservation of energy. And this higher energy one is anti-bonding. Once we have molecular orbitals, we will put electrons in them, and the electrons fill molecular orbitals with the same rules that we have used before. So we will follow Aufbau, Hund's rule, Pauli exclusion principle, and I think that's it. All right. Once we have everything in an MO, there is one calculation that we'll do. We'll do something called calculating the bond order. And this is because when we had something like a Lewis structure, we could just look at the lines we had drawn between two atoms. There are two lines, it's a double bond. Our molecular orbital pictures aren't going to let us do that. So we need to calculate the bond order. And bond order is going to be 1/2 of the number of bonding electrons. So we'll count the number of electrons in bonding MOs minus the number of anti-bonding electrons. So we'll count the number of electrons in anti-bonding MOs. So electrons in bonding MOs contribute to holding the molecule together, and electrons in anti-bonding MOs kind of cancel those out. So they destabilize the molecule in a sense. All right. A stable bond requires a bond order that's greater than 0. So you shouldn't get a negative bond order for any calculation, but if you get a 0 bond order, well, it means no bond. So let's start at the beginning, kind of like we do with everything, and look at H2 as an example. So my Lewis structure, which the Lewis structure isn't going to help us too much, but you will be asked to do some comparisons between MO diagrams and Lewis structures. So it's probably good if you can count your valence electrons and do your Lewis structure. But again, the good news is we're only doing diatomics. Let's label my hydrogens just so that I can keep track of them. So the combine atomic orbitals on adjacent atoms. So each one of these hydrogens only has a 1s orbital available to it. And so what we do is say this is my 1s on hydrogen A. I'm going to combine it with my 1s on hydrogen B. And there are two ways that I could do that. I could combine them in phase, or I could combine them out of phase. So this is my in phase combination, right? They both have the same phase. And when I draw this combination picture, right, if you imagine those two hydrogens are really close together, these s orbitals are going to overlap just a little bit in between. My molecular orbital, it looks like an s orbital, and then it's kind of added together here in the middle, and then here's the other s orbital, right? So this is HA, this is HB, this is my MO from the combination of those s atomic orbitals, and this is a sigma interaction, right? It's the only thing we can do with an s orbital, and it is going to be the one that's lower in energy. Our in-phase combinations always will be. So this is a sigma bonding MO, and you'll see when we label it in some other places, we're just going to write sigma 1s to represent this because it came from the 1s orbitals. The other way that we could combine these s orbitals is an out of phase combination, and this will cover all of my possibilities. So I've got in phase, this is out of phase. Hopefully that's what I said earlier. It is what I meant in case it's not what I said. So if I do this combination, I get destructive interference where they interact with each other because their phases are opposite. So I end up with a place in the middle of my picture of these orbitals coming together that has 0 probability of finding the electron which means my wave function is 0, and we have a word for that, right? A node. And we show it by just drawing a line. So a solid line representing where that node, I mean, technically it's a nodal plane, where it shows up. And on one side, I have my s orbital with this phase, and on the other side, I have my s orbital with this phase. So this is my molecular orbital picture. It is the sigma interaction still, but it's the anti-bonding. And you can kind of get that from this picture, right? It's got a node where the bond would be. So we don't have electrons kind of showing up here because the way that these are arranged, the probability of finding them there is 0. And the way that we designate anti-bonding is with a superscript star. So this is a sigma star 1s. All right, so these pictures are really useful, but I mentioned some things about energy, and other than knowing that bonding is lower energy than anti-bonding, which let's label these lower energy and higher energy. It would be nice if we had just kind of an energy diagram to show these on. So these are pictures of the MOs, right? So if I ask you for pictures, this is what I'd like you to draw. If I ask you for an MO correlation diagram, that means to draw a picture of what I'm about to show you, which is an energy diagram. And it gives us a little bit more insight into what is going on in the molecule, and it's the picture that we need in order to calculate our bond order. So the way that we set up MO correlation diagrams, I need an energy scale. So I'll just be completely honest, it's worth at least 1 point on any question that you get graded on. So make sure you have an energy scale. And then we create these 3 columns that will look a lot like how we dealt with our pictures. So the column on the left is going to be the atomic orbitals for one of our atoms. So we'll just say these are the atomic orbitals for HA. The column on the right will be the atomic orbitals for HB. And in the middle, we'll put the molecular orbitals for H2. And you do need to label your columns when you do these. So the atomic orbitals, that's the kind of the easiest first place to start, right? Hydrogen has a 1s orbital, and the 1s orbital for HA, if I pick this to be the energy for it, the 1s orbital for HB should have the exact same energy. They're the same element, their atomic orbitals will have the same energy. So here's my 1s. And then when they combine, I've drawn the pictures, but I get a lower energy and a higher energy combination. So I get something that is lower energy than the atomic orbitals, and I get something that's higher energy than the atomic orbitals, and it should be kind of equidistant from the two, right? So we're going to say it's the, let me do this in like a gray pencil, right? This distance and this distance should be about the same. I think I did okay. And the lower energy one, this is my sigma 1s. The higher energy one is my sigma star 1s. And that's it. So that's all of my MOs. I had a total of 2 atomic orbitals, one from each column. When I combined them, I had a total of 2 molecular orbitals, which is what we see in the middle. Now I am going to connect these. So I'm going to use these little dashed lines to show that this 1s orbital contributes to these 2 MOs, And this 1s orbital also contributes to these two MOs. You must draw these on your pictures that I'll be asking you to draw. You'll see when we get to some bigger MO correlation diagrams that it can be really important to have these lines in here just to make sense of what's going on. Even though it might feel like it's kind of crowding things, I promise it's actually making things better. Okay, so let's kind of detail what we have here. We've got the energy of the sigma bonding lower than the energy of the sigma anti-bonding. And lower energy means more stable. We've got each atomic orbital contributing equally to the MOs. And we just need to put in some electrons. So I'm going to draw electrons in here, what maybe feels like too many times, but this is the best way to keep track of things. So hydrogen has one electron. I'm going to put that one electron in my atomic orbitals, and you should do this also. So this is what each one brings to the molecule, and it gives us a place from which to start counting to put electrons in my MOs. So I have a total of 2 electrons, one from each, and I need to fill my MOs following all of my rules that I mentioned earlier. So Aufbau, I have to start at the bottom before I move up in energy. I don't pair unless I have to, and I have to spin pair everything, right? That's the poly piece. So my 2 electrons that go in here, I'm going to put both of them in the sigma 1s. I'm going to put one spin up and one spin down, and I've used up my 2 electrons, so I'm done. That's it. So this is kind of hopefully starting to show why H2 forms in the first place, right? We get spin pairing of those electrons. They end up in a lower energy orbital. And let's just calculate my bond order here. 1/2. So number of electrons in the bonding, how did I phrase it up here? Number of bonding electrons, that's what we want to say. So I'm going to highlight this in orange, and then I know it takes me a minute to switch, right in orange. So 1/2 of, there are 2 electrons in this orange orbital. It's my only bonding orbital, minus the number of electrons in my anti-bonding. So I guess let's highlight this in. I don't want to go blue. I don't want to go green either, because that seems like it's giving the wrong impression. Maybe we have like happy feelings about green. Let's go with hot pink. Hot pink. So that is my anti-bonding MO. There are 0 electrons in the anti-bonding MO. So 1/2 of 2 minus 0 is 1. So a bond order of 1 means a single bond. And here it matches with our Lewis structure, so that's great. Okay. So what we use MO theory for sometimes is to kind of predict whether or not a molecule even exists. Kind of with this, we're really just predicting what the bond order would be, but especially in practice problems, they have a tendency to phrase it as something like, does He2 exist? Now, before we go into it, we'd probably predict no, right? It's a noble gas, not really known for forming compounds, but we can prove that now with MO theory. So let's make a correlation diagram. I have energy. I'm going to have helium atomic orbitals. And in this column, helium atomic orbitals. And in the middle, He2 MOs. Helium has just a 1s. It's still in that first row. So this has a 1s. When I combine these atomic orbitals, I'll get a bonding combination. This can be a sigma 1s. And I will get an anti-bonding sigma star 1s combination. I want to dash these to show that those MOs came from these atomic orbitals. What else do I need? I've got my energy label, I've got my column labels, I've got atomic orbitals, molecular orbitals. Now I just need some electrons. Let's stick with gray for my atomic contribution electrons. I don't know, that's a weird way to say it. But helium brings 2 electrons with it, right? So that 1s has 2 electrons, that 1s has 2 electrons. So when I put these in my molecule, I have 4 electrons to work with. I'm going to fill them according to my rules. So 1, 2, because I'm starting at the lowest energy and moving up. This orbital's filled, so I have to go up here, 3, 4. Okay, so let's get my highlights going. This was my anti-bonding, and what did I use? Orange for bonding, orange for bonding. Let's calculate the bond order, which is 1/2 of my bonding electrons, of which there are 2, minus my anti-bonding electrons, of which there are also 2. So a bond order of 0. So this is telling me no bond. Therefore, He2 does not exist. All right, so let's draw some pictures of these molecular orbitals of MOs. So my sigma 1s picture, well, it's going to look like what happens if we bring together a 1s orbital on each atom in a constructive interference way, so a bonding combination. It's going to look like this. And my sigma star 1s will look like what happens when you bring 1s orbitals together in a destructive interference way. So I could shade that side, which means I don't shade this side and I have a node in the middle. And they look exactly the same as what we got for H2, right? And that's fine. They're the same type of atomic orbitals making this combination, so we expect them to look the same.